All right, thanks everyone for coming to the last theory seminar of the semester. Today we have a special theory seminar with our very own PhD students. First is going to be Maryam Abuissa, who's a second year PhD student, advised by Elliot Full and Matteo Riendato at Amherst College. Maryam's also an NSF graduate fellow and an avid climber, as we just discussed.
Okay. Hi, everyone. Thanks for the introduction, Richard. You all know me in here, but I'm Maryam. Yeah, I'm going to present some of the current work that I'm doing with my advisors. So I'm going to talk about null models for hypergraphs given their pairwise interaction. For some of you, I talked about this briefly at a lunch a while ago, so a little bit of it might be repetition, but some of it should be new. Okay, great. So first, just in case anyone doesn't know, I'm going to define hypergraphs. So we have a set of vertices, a set of hyperedges. Hyperedges are subsets of the vertices of any size. We're usually going to assume that the size is at least 2, but you could relax that constraint. This is a picture of a hypergraph with 4 hyperedges. Just this is kind of how we're going to represent them for this talk. So there's a lot of examples and applications that use hypergraphs, like co-authorship, where you group authors by the papers they wrote together, or chemical reactions, where you group like chemicals by when they react together, products that are purchased together, that kind of thing. So there's a lot of examples where hypergraphs are used. But we don't always have a hypergraph. So now I'm going to define projection. So the projection of a hypergraph only has its pairwise interactions. In this case, I've drawn out the projection of this hypergraph. Formally, you have an edge between 2 nodes as many times as they appear in a hyperedge together. We also are going to talk about the flattened projection, which is the same, but where you remove multiple edges. So in this case, we remove that double edge and just put one. Sometimes you only have the projection. So in some applications, the hypergraph information might be unavailable, so you can't really measure it. Some examples of this are protein-protein interaction networks, where it's kind of easier to take pairs of proteins and test whether they interact than to actually detect protein complexes directly. Or human interaction, where it's sensor-based and people, the sensors have like a proximity measure, so you can measure when 2 people are within some distance, but it's hard to say exactly what sets of people are interacting at a given time. And then like also MRI functional connectivity networks, where people tend to use like correlation between brain regions, but it's hard to say about more than pairwise interactions. And then another reason that you might only have the projection is if the data is just unpublished. So there might be some privacy issues, or people might not have known that it was important. This is the case for some graph benchmarks for co-authorship, co-purchase, etc. But the issue with this is that there's some loss of information when you look at the projection. So multiple hypergraphs can have the same projection. In this example, I've drawn out a hypergraph with the same projection, even up to multiplicities. It's a little busy, but this is like 1, 3 hyperedge, and then 3 of size 2. And we'll talk a little bit more about how you can what exactly it means for them to move between. Anyways, so there's some loss of information when you just look at the projection. But like I said, there's some applications where it's all you have. So you might want to ask, can you recover the hypergraph from the projection? And a lot of the early work in this area said, well, maybe if we just take the maximal clicks of the hypergraph, that gives us an idea of what the hyperedges would have been, because hyperedges become clicks, so it seems kind of reasonable. But there's 2 types of error that you see here. So if you have the flattened projection, this error 1, which they called, this is all kind of from a paper by Wang and Kleinberg from 24. They called it nested hyperedges. So if there's a hyperedge, which is a subset of another, you're not going to see it at all in the projection. So there's no way to know that it's there. And another example is the uncovered triangle. So in this case, it looks like V1, V3, and V5 are in a hyperedge together, when actually just V1 and V5 are in a hyperedge together. So what has been shown is that this approach of taking maximal clicks has an exponentially high error in the worst case. So this is not really a good way to recover the hypergraph. So given that there's that kind of impossibility result, yeah, you.
just wanted to, when you say exponential, it happens to roll.
Yeah, it's like a little weird, but basically they showed, I think, like the so the kind of accuracy of the method may be like 1 over exponential in the size of the hypergraph.
Is this for any maximal clique cover you suffer this, or it's just like if you naively take one maximal clique cover, there's always one?
Well, I mean, the kind of the core of it is like you don't have a way to differentiate between, definitely between the maximal clique covers and also between those and like other graphs with the same projection. So if you have some, you know, I mean, either deterministic or random strategy, it's always going to be wrong in the worst case with, you know, high probability.
Okay.
It's a little bit, yeah. It's
okay.
I don't remember the details of their proof, but you could look at it. It's I think I don't remember. I think the process that they choose is either like take one maximal click randomly, or like take or maybe they have like a fixed strategy. I don't remember.
Okay.
Yeah. Anyways, I mean, but the kind of the core of this result is saying like, not only is there information lost by just looking at the projection, there's a lot of information lost, right? There's a lot of graphs which have the same projection, especially when you look at the flattened projection. So it's very, very hard to say that any particular strategy is going to pick the right one with high probability. Okay, so given this impossibility result, previous work has mostly taken 2 approaches. The first one is to assume that you have some outside knowledge and then use standard machine learning techniques. So you might say, well, maybe I have this projection, but I also have another hypergraph from the same application, and so I can learn some of its structural information and then apply that to my reconstruction. Or maybe I have some temporal information and I can use that to say something about like the dynamics of the graph. Or maybe I have like a sense of what I'm going to use it for, and I have some signal from that, and so I can kind of reconstruct it in a way that performs well on that final task. And then the other approach that has been taken is assuming a very restricted setting. So there's a couple of papers that work with D-uniform random hypergraphs. So D-uniform means all of the hyperedges have size D. And this is basically a relatively well-studied class of random hypergraphs, and you can say some things about when can you reconstruct exactly the hypergraph based on the size of D and the density of the network. When can you like tell the projection is different from an Erdos-Schrödinger graph, this kind of thing. But what is missing in the related work is a method which has access to little or no additional information. So it doesn't require you to have a hypergraph from the same application, or especially it seems hard to say like you have a hypergraph from the same distribution, which some of these papers kind of imply. And also gives some statistical guarantees for a user-specified data set. So it doesn't, have any stipulations about what kind of data set you can use. So that's kind of what we're working on. I'm going to talk about some things that we've done and also some things that we're planning to do. So in gray, you can kind of see it not that well, but the last one here we haven't quite fleshed out. But we define 3 novel null models which fix something like the hypergraph projection. So the first one says we look at all hypergraphs with the same projection, which includes multiplicities. The second one says, okay, maybe we don't have multiplicities, so we're just going to look at all the hypergraphs with the flattened projection, and then we need to upper bound the number of pairwise links for a reason I'll talk about later. And then another application we might want to do, but we haven't quite, we're still working on it, is what if the projection is more uncertain? It's like something like the probability of links between nodes, and then can you have a null model that addresses that? We give algorithms to sample from these null models, and then we hope to, wow, you really can't see the gray. That's too bad. We hope to show the effectiveness of these null models in reconstructing a hypergraph given its projection. So that's kind of what we talked about so far. And then another application that we want to look into is how can we use these null models to analyze how important the non-pairwise structures in the hypergraph are for a certain data set or application. I'll talk a little bit more about that later. Okay, so first I'm gonna go through the null models, and then I'll talk more about the applications, and then that's good. Okay, so there's 2 null models that I want to introduce today. The first one is the most simple. It's all of the hypergraphs with the same projection, and the distribution is uniform. I will give a sampler for this in a bit. And then the issue with this is that in some settings you don't have the multiplicity. So if you think about like the protein-protein interaction networks, when you measure two proteins, it's not telling you like how many complexes include those two proteins. It's just telling you whether or not they do. But in this case, now if you think about like back to those errors, if you fix the flattened projection, the number of hypergraphs that have that projection is infinite, right? You could add as many kind of sub edges or multiple edges as you want, and it would all have the same projection. So we need to bound the space somehow to use a Markov chain Monte Carlo process. So the way that we do this is we say the null set is all hypergraphs with the same flattened projection, and we upper bound the number of pairwise interactions. And again, we have the uniform distribution. You look confused.
What is a pairwise interaction?
Oh, just like an edge between two.
A shared edge between.
Yeah. Or like, yeah, in this case, like when I say the number of pairwise interactions, it's like you could say the number of edges in the projection with multiplicities. Yeah. Any other questions about that? No, you look confused.
Sorry, this K
K is like a
true projection or before?
So, okay, yeah. So it's a little confusing because we're saying like we're fixing the flattened projection, but when we have an actual hypergraph, because we're sampling it, we can calculate its projection. So we're bounding the size of the projection of like our current sample. Yeah.
So after projection, it has to have most K edges.
Yeah. You could imagine that you might want to bound the number of hyperedges, but it turns out that it's much more complicated. So we're just doing this. Okay, so these are the two null models that we're mostly working with. I'm going to go through how the first one's MCMC process works, and then I'll talk a little more about applications. So we said we want to fix the projection. I think that, yeah, this I might have talked about at lunch a while back. Anyways, we're going to have two moves to move between hypergraphs. The first is a move that I call separate. So this basically takes the purple hyperedge and it takes node 2 and it takes 2 out of the purple hyperedge. So now the purple hyperedge has 1, 3, and 4, and there's like all of the kind of 2 edges, which is what I'm calling edges of size 2, that you need to complete this click, basically. So these have the same projection. You can convince yourself. And you can imagine if you like removed all of these nodes, you would just end up with the click, which is in the projection. Then there's another move is the reverse, which is combine. So it's just you take some edge, in this case the purple one again, but we're looking on the right side, and you take a node where it can be added, and then you add and remove all of the kind of pairwise interactions that were necessary for that. To sketch irreducibility, to give you an idea of why this Markov chain works, we need to build a path from between 2 arbitrary hypergraphs with the same projection. And the way that we can do this is pretty simple. We can just take every hyperedge and separate it. And by doing that repeatedly, we get the projection. And then the second hypergraph also has that projection. So we can just combine all the hyperedges until we get that hypergraph. So that's irreducibility. Okay, great. So these two null models allow us to sample many hypergraphs with the same projection. And specifically, we're taking the maximum entropy distribution with this desired either projection or flattened projection, right? The uniform distribution has maximum entropy over this constraint. Are you convinced?
No, are you going to tell us about conductance canonical path?
No, so yeah, so that is in the context of future work. It seems like it's pretty hard to analyze the mixing of these chains. We've thought about it some, but yeah, we haven't made progress on it yet. Yeah, so yeah, there's a question of how long does it take to actually run this Markov chain to do this, which we haven't quite answered. But given that you run it, we're kind of just assume you run it for a very long time, you get a sample which is roughly from the maximum entropy distribution. You can use this in a number of ways. So a lot of the previous work basically just says like, we're going to construct one hypergraph which has this projection. The thing that's nice about our work is it says we're going to actually give you a distribution of hypergraphs with this projection. So if you are in an application where all you have is the projection, you can use this to estimate some distribution over the desired quantities, which might be, classifying the nodes or predicting new hyperedges, link prediction, or anomaly detection. And then you can kind of, because this is you get a distribution over that, you can then decide how you want to use those things. And And then the other application, which I mentioned briefly earlier, is you might actually have a hypergraph. And the cool thing that this null model allows you to do is compare your hypergraph to all of the hypergraphs in this null model. You know, you sample some number. And it gives you a sense of how important the more than pairwise interactions are if you do, you know, if you have some task or some measurement. And it might also tell you like how exactly the more than pairwise interactions impact this measurement or something. That's kind of cool. And the nice thing is, in some cases, you might find, in a lot of cases, people have found that basically the hyperness matters a lot. But if you find that it doesn't, you can like only store the projection, which is easier. You can use graph algorithms on the projection, which there's kind of just more abundant graph algorithms. So that's also kind of neat, I think. Okay, great. Then future work. So yeah, we want to look at the experimental performance of both the reconstruction and the null modeling applications of these null models. We want to analyze the theoretical mixing properties of the samplers. Yeah, hopefully we can, but it's definitely hard. And then some future work that we probably won't do, but is still interesting, is incorporating temporal information. A lot of these projections do have them into our null models and sampling algorithms, and just defining generally richer. Oh, this is slightly a typo. Richer null models for this space and algorithms to sample from them. Short recap. I'm just recapping what I talked about. So I talked about 2 novel null models to sample from null models which fix the hypergraph projection. One which fixes basically the projection, and one which fixes the flattened projection and also bounds the size. And I showed algorithms to sample from them and some applications. That is all. Thank you. Do you guys have any questions?
Is it clear why the stable distribution is uniform?
You can basically modify the probabilities, collapse, so that it's reversible, and then it is uniform.
By carefully choosing.
Yeah, basically you look at like, okay, if I, given I'm in this graph, how likely is it that I'm gonna like combine this? And then given I'm in this graph, how likely is it that I separate? And then you want to make them equal. So you take like, I think the minimum of like some ratio, 1, or the max, yeah.